All right, hello everyone. Let's get started. So, I hope everyone's having a good night, a good week 5. I know it's been kind of a crazy week, so hopefully tonight will be fantastic to make up for any stress that y'all may have been feeling. Go ahead and sign in on that QR code. I'll be talking a little bit more about that later, but it's pretty important for us to be able to prepare better for future events. But anyway, if you are here for the AIChE Projects Welcome Night Fall 2020, you are in the right spot, and we are super excited for you to be here. I'm Eleanor Quirk. I'm the Program Director of Projects, and I'm very happy to bring this event to you tonight. So let's get started. If I can click through my slides. So yeah, just a few starting notes. Please keep your microphones muted. That just helps us avoid background noise. We will have some Q&A later. You're definitely welcome to have your mic off for that. But until then, please just have your mic on for that, but please keep it off until then. Another thing is this event is being recorded. By participating in this event, you consent to being recorded. If you have your camera off and your microphone off the entire time, you won't be recorded at all. Another note is that the poster session will not be recorded. Only from here until the poster session we will be recording, and the recording will be posted on our website and on our YouTube channel. So just a quick thing, that is the sign-in link again in the corner there. AIChE has a fall quarter raffle, and it's very exciting. The first prize is sorry, oh my gosh, I can't speak. Apple AirPods, that's what they're called. And the second place is a Keurig coffee machine. The third place is an air fryer, which is very exciting. By signing into this event, you get a chance to join this raffle. And I think it's one of the last, if not the last event that you can get a raffle ticket for. So make sure you sign in. It's that QR code in the corner. And we will have that at the end of the event as well, in case you haven't done it. But I highly encourage everyone to sign in. So with that said, let's get on to the more fun stuff.
Alrighty, everyone, just so that you're not super surprised by anything we throw at you, today we will first and foremost be welcoming you to AIChE Projects if you are new here, and telling you guys all about ourselves. And then we will also have a small social component of speed friending in which you will be placed in breakout rooms. More details of that will come later. We will then segue into our actual project team presentations in which each project team will be presenting themselves. And then we'll also give some of the Spring Showcase Awards that we had last quarter. After that, we will be talking a little bit more about the application and interview process for those of you who are looking to join us in the future. And then we will also be having a poster session in which you guys can talk to the teams individually. So I hope you guys have a great time here. Take it away to the next slide.
Yeah, so just want to give you guys a little bit of an introduction to the organization that is AIChE Projects. So AIChE Projects is a projects program sort of under the governance of the American Institute of Chemical Engineers at UCSD. And our organization sort of aims to address pressing environmental issues sort of through student-led research teams. And so essentially, AIChE Projects provides opportunities for undergraduates to, gain all different types of experience, whether that's research experience, hands-on work experience in terms of, machining or otherwise, and then additionally problem solving and teamwork experience. So it's a really, really great opportunity, I think, for undergrads to sort of grow their skill set and also, maybe solve some environmental issues along the way. And so as an organization, we heavily encourage technical and professional growth. We host multiple technical workshops each throughout the year. So usually that's 1 or 2 a quarter. And then there are, professional showcases. And then also project members are technically members of AIChE and are able to attend the pro dev events there. And then sort of some of the other cool opportunities that AIChE has for its students.
So hello everyone, I'm Jared. I'm research coordinator for AIChE Projects. Just a quick note about official statement of who we are. We promote excellence in engineering, education, and stimulate collaborative efforts among industry and professional societies by promoting team-oriented, hands-on experiences for its students alongside local nonprofit organizations and industry. That is kind of our essence as an organization, summed up into one nice and tidy sentence. But if you would like to know more about us, or pretty much everything about us, feel free to visit our website, aicheprojects.org. Everything that you could possibly want to know about AIChE Projects is on there, and if it's not, then you can reach out to any of the folks that you will see on the following slide.
Hello, we just want to take another moment to introduce ourselves. So I'm Eleanor, I'm the project's program director.
My name is Nick Dorn. I'm the project's program manager.
I'm Jared, I'm the project's research coordinator.
My name is Diana, and I am the assistant program director.
Hi, I'm Hriday, and I'm the assistant program manager, and it's great to see you all here.
Hi, I'm Harleen. I'm the assistant program manager as well.
Hi, everyone. My name is Joy. I am the assistant research coordinator.
Yeah, collectively, we are the leadership team of projects, and we are here to bring the whole projects program to you as best we can. If you have any questions about projects, please feel free to reach out to any of us. We're always happy to talk about projects.
All right, so this is just a brief overview of all of our 5 project teams. So that's essentially a list of all the project teams we have. As Nick mentioned before, AIChE Projects mainly works toward addressing environmental issues. So all of our project teams also work towards addressing one or the other environmental issue. Some of our project teams work in renewable energy, so they work in different aspects of how to generate renewable energy sources, or how to harness them and make them more accessible. And while some of our other project teams work in water purification, so to how to make potable water more accessible and easier to purify. So yeah, that's essentially the list of all of our project teams, and then more details can be found in the presentations later on.
And this year, we decided to introduce a new team which focuses on ethanol extraction. The traditional method to extract ethanol includes distillation, which is a highly energy-consuming process. There are many ongoing research on an alternative method that can bypass the distillation processes, including using enzymes produced by microbiomes or using different starting materials. Because of the variety of directions that this project can proceed, we believe this team is of great potential and flexibility. It's a completely new team, which means there are no project managers nor members, but leadership will provide support to whoever is interested in this area in terms of setting concrete plans or connecting you to possible resources. Moreover, it kind of bridges bioengineering with chemical engineering, and so this team will be the first official interdisciplinary project in AIChE. And we'd like to say thank you to Digvijay Jani for informing us about this topic.
So we have a really important and fun concept in our AIChE Projects Welcome Night in person, which is socializing and getting to know each other and kind of getting to know other team projects as well. So we came up with a fun and unique way to make it happen over Zoom, and it's kind of going to be like speed dating, but speed friending. So we're going to put everyone into random breakout rooms of 4 to 5 people, and just kind of introduce yourselves, name, major, year, and then we'll send you guys 2 questions that are pretty unique. So you can answer those. And yeah, Jared, do you want to add everyone into breakout rooms? Also, if you don't want to be social, completely okay. Just come back at 7.
Okay, thanks everyone for your patience. It looks like most people have gotten back. Sorry for that technical problem. We don't know what happened, but hopefully it won't show up again. Anyways, let's go ahead and get started. If you know anyone who's still in a breakout room, please message them and just let them know that we're getting started. But anyway, our first presentation will be from phosphorus wastewater treatment. Fuel cells, CDS, PWP, and AWT will go after them. We will be doing a Q&A session after every presentation. If you have a question, go ahead and put it in the chat either during the presentation or wait to unmute for after the presentation. Yeah, without further ado, let's welcome PWT.
I was muted the entire time I was talking, but hello guys, can you please let me know if you can see the presentation?
Yes, you can see it.
Okay,
Yeah.
thank you. Parts of my screen are a little blocked because of Zoom, but it's okay, we'll work with it. Hello everybody, this is phosphorus wastewater treatment. We also go by PWT. Just to introduce some of our members so that you have some faces to the names. My name is Diana. I introduced myself as part of leadership already. I am also one of the PMs for this team. Joy, would you like to introduce yourself?
Yeah. Hi, everyone. My name is Joy, and I'm the other co-PM for PWT. We're here to talk about the purpose of our project and the methods we're using.
So our other team members are also Eleanor. We all have Nicholas, Stephen, Jake, and Arturo. You guys will be hearing a little bit from them in just a little bit.
Okay, so hi, my name is Stephen, here to explain basically the general premise of this project. So the issue we have with wastewater is that it leads to excessive nutrients that enter the aquatic environment, and that leads to algae growth on the surface. And what essentially happens when you have a bunch of algae on the surface is that it prevents sunlight from reaching the bottom of the lake, where you have other plants, fish, and other life down there. And without sunlight, those animals and organisms eventually die off and they start to decay. And this leads to oxygen being used up by bacteria here. And once the area becomes oxygen deficient, then it creates this negative feedback loop in which organisms continue to die off. And our goal is to try to reduce the effects of phosphorus on the environment by trying to remove it from wastewater.
Hi, everyone. So unfortunately, with this explanation about what we're trying to do, unfortunately, we have realized that it's actually affecting most of the inhabited continents on this Earth, as you can see that lists the Europe, US, and all that other good stuff. And specifically in the US, testing has not yielded great results. Most of the year, we see increased levels of phosphorus in the water, which is no good. Specifically in SoCal, 80% of the year, there is an unfortunately high amount of phosphorus in the water.
Since phosphorus is the primary cause of eutrophication, our project thus aims at recovering the phosphorus from wastewater and regenerate that phosphorus to some other forms that can be readily applied. The method we're using right now is called ion exchange, which is essentially a type of chromatography that can separate all charged particles, including phosphorus, which exists as negatively charged groups in water. Among the many forms of ion exchange methods, PWT uses anion exchange resins in a flow system to regenerate phosphorus. Resins are often beads that have an internal matrix structure that houses charged molecules to attract particles of the opposite charge. And in this case, when the phosphorus wastewater flows through the system, the negatively charged phosphorus will be attracted to the positively charged groups in the resins, the equivalent of a stationary phase, and replace the mobile phase. In this way, resins can be regenerated by replacing the mobile phase with phosphorus, meaning that it can be separated from resins once again. And we're going to talk about our experiments. Does somebody want to take on?
Yeah, hello. So I'm going to tell us a little bit about the results that we've been able to have so far. They've been a little bit stunted because of COVID, but we still have some things that we want to talk about. So first of all, we did a proof of concept first trial. At this particular time that we did this experiment, we did not have a column or an exchange column, so we used a beaker and batch reaction instead. We added resin beads to a prepared solution of potassium phosphate, and that caused the phosphate to bind to the beads. The beads were then added to an NaOH solution, which allowed the phosphate to be released from the beads and thereby regenerating the beads. We then added, we then put calcium hydroxide in with the phosphate, precipitating out the phosphate as calcium-free phosphate 2. As you can see on the right there, that's quite a bit of powder that we have in those little glass beaker things, which indicate that a lot of phosphate was removed from the system, which is proving that our method works.
All right, everyone, we'll be talking about our slightly less successful trial. So when we were doing our background research for our, the resin, we found out that there's something called hybrid anion exchange resin, which was basically some research teams were able to graft iron oxide onto their beads. We tried this by our homebrewed method of grinding up iron oxide and putting in an acid solution and putting it with the beads. But we found out that this actually made the beads recover less phosphate. So it's kind of a failure, but we did get some positives on it because we were able to determine that there's other errors in general, namely that the calcium hydroxide is not very soluble in water, so that the calcium phosphate may have been calcium hydroxide. So now we have some better information from our failure.
All right, so in the third trial, we were testing for residence time, which is testing to see how long the experiment took to capture phosphate. So we actually found that over time, actually, it was detrimental to phosphate capture. And this is due to chemical equilibrium reactions that cause the phosphate to both be absorbed and also released. So we didn't want it to be released, we wanted it to be captured. So what we did also find, though, was that residence time was about 1 minute, and this was doing batch setup experiments. So this meant that we can actually move down to a smaller scale and have a column set up and hopefully like tweak the experiment more and get a better residence time. We want it to be in the tube as short as possible.
Alrighty, so some plans that we have for this year, are to continue to learn about ion exchange resin and how we can optimize the system that we currently have. We hope to move from the batch reaction to a continuous flow reaction. And we also hope to reach out to biology labs so that we can help them reuse and reproduce the phosphate that they are using, so that it doesn't go out into still water in our ecosystems. With COVID, of course, everything has been quite slow moving, but all in all, we're taking it in stride. We're learning more about ourselves and about each other and just having a good time doing it. So that is the end of our presentation. If you have any questions, please let us know now, put it in the chat. And I hope you guys come to our breakout room for poster session.
If anyone has any questions, feel free to unmute or pop them in the chat and we will answer them right away. And if there's no questions, we will go ahead and move on to fuel cell.
Sounds good, sounds good. Let me share my screen real quick. This guy right here. Okay, share. I think I'll just click present. Yeah. Is everybody able to see this presentation? Actually, if you can't see it, just say, I just like mention the chat. Okay. Well, cool. Seems to be no issues. Cool. So my name is Nick Dorn, and I am one of the project managers of the fuel cell team. And I am joined in this presentation by Joyce Shen. Joyce, do you want to introduce yourself?
Hello, my name is Joyce, and I'm the other PM for fuel cell. My internet's kind of rough right now, so if anything goes wrong.
Yeah, so I guess we'll get started. So our team, our team nickname is Fuel Your Soul, and it's sort of an exploration into renewable energy storage. So basically sort of seeking to understand novel ways to be able to store energy that we can harvest from the sun. So let's see, let's get into it. Joyce, I think this is you.
Okay, so to give you guys some background, recently we've and should I even give a better background of like how everything works in general? Okay, so wait, Nick, can you go to the next slide?
Yeah.
Okay. Yeah, so our team is fuel cell, and we mainly work with hydrogen fuel cell. But honestly, what exactly is this hydrogen fuel cell and how does it work? So I like everyone to imagine a battery, and this battery basically energy is produced by the reaction between hydrogen gas and oxygen gas. And as you can see from this photo, hydrogen gas comes in from the anode side, and it basically gets separated, and the electrons goes through, flows through the other side, and the hydrogen gas or the hydrogen particles goes to the cathode side, in which interacts with the oxygen there, and in results they form water, and basically that's the reaction that goes on in our fuel cell, and that's how energy or electricity is generated. Like it's generated through this process. And so Nick, if you can go to the previous slide.
Yeah, definitely. Cool. All right, there we go. Oh, well, I can't really go back, but we can keep going forward. But basically, yeah, so this is sort of some of the more,
no worries.
I guess, some of the more tangible aspects of our project with some nice photos. But yeah, so basically, part of our design is essentially a reversible fuel cell. And because basically, if you can essentially take in, if you could sort of apply power to sort of the, like voltage source in the fuel cell, you can sort of run the fuel cell in a reverse manner and actually generate hydrogen given the correct ingredients. So basically, what we've done as a team so far is we have 3D printed our own plastic plates, which were then painted with conductive paint and electroplated. And so our plating designs are made with reversibility in mind. And so essentially they can be run both ways, either in the forward direction or the reverse direction, which is sort of very conducive to how this project works, as you'll see later on in the presentation. And so, yeah, so we originally had a fuel cell that only ran in the forward direction, but ended up getting a new proton exchange membrane materials in order to allow for a reversible fuel cell. So we've actually, we actually have a functioning fuel cell, which we can sort of apply a current to and generate some hydrogen. So it's, it's pretty cool little system. So yeah, so basically, originally starting out with the forward fuel cell, we've moved away from this design and shifted focus to a dedicated electrolytic cell to produce hydrogen gas. So yeah, I guess this is a picture of our electrolytic cell. So you can see sort of PVC piping and various different nozzles. And so basically this sort of area, the pipes are filled with potassium hydroxide in solution. And then essentially you can apply a current to the fuel cell, and you'll get, and then hydrogen essentially starts rising up towards the nozzles at the top, and the eventual goal is to essentially harness the hydrogen that rises up through those nozzles and be able to store it. Cool. So yeah, so I guess I can speak about hydrogen storage really quickly. So basically, with that hydrogen that we generate through the reverse electrolytic cell, sort of one of the major facets of this project is storing that hydrogen. And so we have decided to sort of look into a very novel hydrogen storage method, and that is metal hydrides. So there are many different metals which sort of complex with hydrogen and can actually store hydrogen in the metal's solid state. And so, yeah, so basically, we're basically looking into sort of using lanthanum pentanickel, one of the many metal hydrides, but one that we've identified to be super effective for our purposes. We are sort of looking into, putting that into a tank, and then essentially seeing if we can store some hydrogen, and then, by changing the pressure, be able to release it and run it back through a forward fuel cell. There we go. Going. There we go. I guess, Joyce, do you want to talk about the hydrogen storage design?
Well, this is pretty much, you kind of covered it pretty much already, but basically in our hydrogen storage, we will need the material for the tank itself. Like inside, we will need the lanthanum pentanickel to store the hydrogen gas. And then we also need appropriate sizing, because we don't want it to be too big so that it's hard to measure pressure, or it being too small so that it's not very safe. And we also need to have the check valve. We want to ensure that we can reverse the process so that we can achieve the both way energy process rather than just the one way. That's pretty much it. So we can move on.
Yeah. Cool. Nice. Yeah, so this is sort of an example of a hydrogen storage system. So you can sort of see a diagram here. Doesn't need too much explaining, but essentially you have the inlet, outlet hydrogen, some thermocouples, the vessel which contains the actual metal hydride. And then this is obviously a very advanced system with a lot of different temperature controls, because temperature is obviously one variable that is pretty important when sort of adjusting the pressure and sort of adjusting the adjusting the ability for your metal hydride to be able to contain the hydrogen. But yeah, so for our initial experiments, we're looking for something a little bit more rudimentary, but sort of the same principles. Yeah, so this is just a comment on system integration. So basically the way this all works together is that you basically have the solar panels, which would basically generate a current, run it through the reverse fuel cell, generate hydrogen, store it for a rainy day, and then, when the time comes, run it back to the forward fuel cell and generate some power. So sort of, in that manner, basically, taking solar energy and finding a novel way to store it. So yeah. And there's a quick mention in here about sort of a previous iteration of the project, which was a solar umbrella. And so that, there's been many iterations, and sort of the process has evolved very much past that. And so now we're shifting towards using the solar power, the same idea of a solar panel awning, but with the goal of sort of generating hydrogen through a fuel cell. Cool. Joyce, if you want to talk about moving forward.
Yes. So as we have shown from the previous slides, we have the electrolytic cell already built. And now our main focus is to design and implement the hydrogen storage mechanism, and to finalize that design, and work to see if, like, oh, how much do we need the lithium pentanickel, how big do we want it to be, how much hydrogen gas we would be able to produce from our electrolytic cell. All these are these are the components that we need to go and measure and to keep track of. And eventually also want to just connect everything together, the fuel cell, how exactly it works. And obviously there's going to be a lot of details in it that we need to kind of fix a little bit, give it a little notch of adjustments. But ultimately we want to be able to make it so that it's applicable for on-campus use, basically.
Awesome. And so basically, we are currently in the build phase, but since COVID happened, we've sort of had to shift our team activities a little bit. So currently what we are doing is taking a Fusion 360 course as a team, basically just familiarizing ourselves as a team with CAD, and sort of enabling ourselves to be able to design various components of our fuel cell project, whether that's the plates or different housings for some of the different aspects. But yeah, so that's sort of what we've been up to. Research is always ongoing. It's something that we're definitely going to be ramping up here soon. Basically, planning out some of the experiments to test the viability of metal hydrides, of specifically lithium pentanickel, and sort of the capabilities of what that can do for our project. So yeah, there we go. Cool. So the mouse is not working very well, but thank you to AIChE Projects leadership, AIChE, and the fuel cell team, everybody who's contributed to this project in any way. And yeah, that is sort of our team. Any questions?
Hi, I have a question about the metal hydride.
Yeah, go ahead.
So how accessible is the lanthanum pentanickel metal hydride, and how expensive is it to use it in the storage mechanism for fuel cells?
Yeah, so I mean, it's something like $77 for 10 grams. It's not like an absurdly expensive or rare metal. It's obviously not aluminum foil. But yeah, so it's I mean, it's sort of just a standard reagent you could buy from various inorganic chemistry suppliers. So yeah, I mean, I hope that answers your question.
Thank you.
The question in chat, is it like an alternative to a battery?
Yeah, so yeah, in a way.
Response to the question in the chat. Oh, sorry, I lagged.
Oh yeah, no, Joyce, you can, you can take it.
Okay, yeah, in response to the question in the chat, yes, I think our fuel cell, one of the biggest benefits to it is that it will be a battery that has pretty much no waste, because then we'll be creating water and steam. And this is a little off topic, but I actually was watching some video today, and then I came across this one where he was saying that, oh, like hydrogen fuel cells are like kind of silly because then like hydrogen storage is so difficult and like, oh, it's not efficient, things like that. But I think like even today, the lithium batteries, eventually you'll create waste from it, and you also need the metals to be able to create them. But then for us, if we just have that amount of metal hydride and we have water and air, which is literally everywhere, I guess in a sense everywhere, and we can create a battery that's reusable and renewable and doesn't create that waste. I think it's a good idea that like we can work on this project, and like, yeah, that's basically the idea. Don't know if I answered the question, I just went too much on a tangent.
Any other questions before we leave for the evening? Cool. Well, thank you guys for listening, and really appreciate the questions.
All right, CDS, I believe you're up next.
Okay, let me share my screen. Can you guys see that? All right, cool. So yeah, so we're the crowd desalination team, and my name's Kyle, and I'm one of the 2 PMs of the CS team. And I guess the general background of our team is that we're currently trying to engineer a device where we can convert ocean water into usable pure water.
So kind of a background on where we got our research from for this idea. It was off of a patent by Dr. Buxbaum. He had this, you can see the figure, he had this prototype where in the bottom left corner, it starts where the seawater is put in, and then it goes into a freezer, cooler, melter, washer, and then it comes out as brine and seawater, or fresh water, my bad. And so basically he had this pretty nice system where we could kind of build a foundation for our prototype. But the only problem was that it was kind of expensive for the type of project we were trying to go for. But we kind of got a good idea that we wanted to use ideas off of thermodynamics, fluid mechanics, and heat transfer. And so next slide, please. So we made this new system. So the outside, the gray part is like a foam container. And then in the inside is dry ice and alcohol. And that pretty much cools the seawater to the temperature that we want it to be at. And then we have a cylindrical vessel. For us, we're using like a Arizona bottle. And we've been trying to keep it like well insulated. And then there's a stirrer that we're using in small increments of time. And we hope to make it automatic. We'll talk about that later as well. But yeah, so this system is a pretty easy design and not too expensive either, and it's easy to transport. But yeah, and we kind of use like a progressive freezing, as I already said, like stirring in increments of time. Yeah.
Hello, my name's Eric. I'm one of the other PMs for CDS, and right now, the previous prototype from the very first group, I believe it was 3 years ago, implemented a machine, an automatic stirrer, which stirred the seawater. But the issue, next slide, please. The issues for that prototype was that they weren't able to freeze the seawater, and purchasing dry ice was very not sustainable and very expensive. And the vessel they used was acrylic, which prevented the coolant to freeze the seawater. And the trials were extremely long. I believe it took them 5 to 8 hours just cooling the seawater. And the main issue for that past prototype was that they were unable to freeze salt water. With our current prototype, next slide, please. We changed the container to aluminum, as Harleen said, and we introduced a new type of a solution, which is isopropyl alcohol fused with dry ice, and which we were able to freeze the seawater, and we brought the temperatures down to, I believe, negative 98 Celsius. And right now we're using sustained freezing, meaning we're trying to keep the coolant to negative 10 Celsius and negative 18. And we introduced a new pump which aided in the coolant circulation. Next slide, please.
Hello, my name is Alex. I will tell you a little bit about our test results. So, spoiler alert, we actually did get it to freeze, and we were able to reduce the salt ppm in the solution. Not close enough to drinking levels, because that's very, very pure, but I think it was just kind of a proof of concept for us. And we found also that running longer processes, so around like 30 minutes, usually yields more purified ice and hence a reduction of salt compared to kind of just rushing through it. So next slide, please. So now we basically just want to lower ppm values of salt in our frozen water. And so we have a couple different ideas for how we might do that. First of all, we want to create a steadier temperature gradient. There's a couple different ways to do that. I know some of us are looking at different container designs kind of to change the heat transfer between the coolant and the actual solution. And we want to make the process autonomous because the previous groups, their automated stirring mechanism, they got rid of because it wasn't freezing at all. And so now we would like to reintroduce an automated stirring mechanism now that we can actually produce ice. So we're looking into that and some automated processes for refilling the vessel with new cold coolant, because currently we kind of have to drain it and then put in new colder coolant in like every so often. And also looking for like an automated way to remove ice, because currently it just freezes along the sides of the vessel and it's kind of difficult to get out. We kind of have to like scrape it or like squeeze the container to get it to break. And another thing is we're looking for a way to automatically measure the temperature using like an Arduino circuit, because in the past what we've done is we've had to stick a thermometer into the coolant, measure the temperature and write it down, then dry it off, then stick it into the solution, measure the temperature, dry it off, and then repeat. So obviously it'd be a lot faster to have and easier to have a computer do that for us. So we're looking into that as well. We're also looking for a more reliable coolant source. I kind of touched on this earlier, but essentially what we're doing is freezing the coolant with dry ice and then putting the coolant into our container. And that's pretty inefficient. We'd like to find a better way to cool our coolant or like keep it cold so we don't have to go through tons of dry ice, kind of like Eric was saying, is very impractical. Yeah, and so then next slide. So for our second phase, essentially we're just looking to scale up. Once we can reduce our ppm levels, we're also interested in seeing how the same process works at bigger sizes, because volume and surface area don't scale proportionally, right? So we're kind of looking for the best ratio of size to efficiency before moving on to the third phase, which is next slide.
And I'll talk about this phase. Is that like once we finally get through phase two, I guess our ultimate goal is to ultimately like create like a multi-tube system where we can essentially like yield as much potable water as possible. And then like also just wanted to determine like how much energy is needed to just produce to create this new potable water, and we just compare with other I guess sources, desalination methods such as like reverse osmosis. And like once we create like our like a final cryo desalination system, like we'll determine the cost and see if it's like whether it is worth it to pursue it on a large scale role. And then I guess like I can talk about like what our team has been doing during this time. Currently, we're at the stage where we're just trying to redesign our prototype and such, and overall just create more of a sophisticated design. And at the moment, like all of our testing has been halted. I guess like, yeah, cross our fingers, hopefully we can start in the spring. If not, that's all right. We'll like currently we're just trying to just research and see how like different like methods of like how we can improve our design. And then once COVID ends, we can just start testing and see what works and what doesn't work. And as well as like our, like I said, like research focused on this overall, just redesign our prototype to make it more sophisticated and overall see if our results improves, as well as our team is trying to learn Arduino in order to, like what Alex says, like implement some sort of automated stirrer, plus like improving our overall experiment through measuring the temperature automatically. And I just want to thank Tess, AIChE Projects, and the leadership, and Professor Ping Liu for supporting us. Yeah, do you guys have any questions? I can't see the chat right now, so.
I have a quick question.
Mm-hmm.
So y'all were saying that the aluminum can was predominantly the vessel for holding the salt water. I was curious if y'all have experimented or seen any other research about other vessels to potentially hold the seawater, and that would potentially increase or decrease that thermal conductivity.
Yeah, at the moment, like I guess from what Eric says, like a previous team experimented with acrylic as the vessel, but the problem was that it wasn't, because I guess the heat transfer properties weren't that great. It caused the water to not be able to freeze whatsoever. So that's why we're just experimenting with the aluminum can at the moment, because right now we're getting like good results. So water is freezing, plus 2/3 of the salt is removed from the ice. So that's why we're using this vessel at the moment. Any other questions?
We are running a little short on time, so thank you so much for presenting CDS.
Yeah.
If anyone has any questions, feel free to drop by their poster session later. But for now, we're going to welcome PWP to the stage.
Hello, everyone. Okay, can I get a yes if everyone can see my screen okay? Okay, cool. So hello, everyone. My name is Michelle. I'm one of the PMs on portable wind power, and our team is building a small scale wind turbine that is portable and will be used to charge small electronic devices such as phones, tablets, and laptops. So our team does focus on renewable energy and wind power in particular. Back when other teammates were designing the project, they really wanted to utilize La Jolla as a location and the proximity to the ocean that we have, and all those La Jolla cliffs that provide us with a lot of wind. And also, there is currently a wind turbine on campus in the Warren Canyon, but not a lot of people go back in the Warren Canyon, so it's not too accessible, so there's not too much traffic. And yeah, let's see. So here is our design. We're currently in the beginning building stages of our project, but of course that's limited due to COVID. So here's some of the visuals that we have. Essentially, we're building 2 turbines in one with a universal base, and we'll be switching out the different assemblies onto the base. So we have 2 sub-teams actually who focus on each assembly, and one is horizontal and one is vertical. And once we have a solid prototype, then the plan is to test both of the different assemblies and then determine which one is the most efficient. And from there, we'll improve the one that is the most efficient. So, yeah. Here's a bit of the modeling that we've done using SOLIDWORKS for some of the parts for our project. So here you can see some of our turbine blades for the horizontal team. And here's also the hub that is kind of the cone that sits in the middle of the horizontal turbine too. And then here you can see we have one of our schematic drawings. This is the acrylic box that will house all of our electrical components, such as the generator, the battery, and the Arduino. And out of this one opening, that's where the vertical axis turbine is going to come out, and it rotates on this gear system. So, and then shifting from vertical to horizontal, we're not doing both of them at the same time on the same setup. It's kind of, we're doing each of them individually. So when we want to switch from vertical to horizontal, we'll move the generator inside to come out of this opening, and that's where the horizontal assembly is going to come out. And here you can see, so winter quarter, our vertical team used the laser cutter in the Envision studio to cut out their gear system. So that's pretty cool. Let's see. Yeah, here is our team members. It's pretty cool because we have one electrical engineering major and a nano engineering major. So we're not all chemies, which I think is one of the coolest part about our project. We've also had some mechanical engineers in the past, so we're a pretty diverse team. But now I'm gonna switch it off to, or hand it over to Henry. Yeah.
All right. Hi, guys. So through our research, we've kind of been able to hone in on a few key skills that Michelle talked about earlier that have kind of allowed us to go in the right direction with this project. And that obviously includes some Arduino, CAD/SolidWorks, and the laser cutter, which we had just talked about previously. So to go off our progress from last year, that entailed having that universal base designed, which is going to house both the vertical and horizontal turbine. We received project funding, which is obviously very important because you kind of need that to collect the materials and make any of this happen in the first place. We began building both the turbines. Like you had seen before, a lot of the modeling was done initially in SolidWorks to make sure it would actually function properly. So like Michelle had mentioned, we went into the Envision studio and used the laser cutter with pieces of acrylic to cut out some gears that are going to be able to convert that mechanical energy into actual usable power. And we began to set up an Arduino LCD display, which is kind of cool because it's allowed us to display the power output of the turbine. And more recently, we've been kind of picking up on, again, to have it display possibly, other important data and information, which I will talk about in a bit. So yeah, COVID has definitely thrown a curveball at most groups, including ours. So we've decided to take an alternative route to kind of still make it to that end goal. So that includes the Coursera Wind Energy course, which I found to be very helpful. I feel like a lot of my team members too have found it pretty insightful because it kind of just, helps you learn about real world applications. And it's even allowed us to talk about some techniques that we kind of want to see if we can implement into our own project. We've also been doing some LinkedIn learning courses, which is a bit more on the practical side and kind of provides us with some skills for the future. We've done some virtual prototyping, once again with CAD, and we've kind of had some brainstorming sessions just to talk about what we want to maybe implement if we have the time or the funding. So that's kind of fun. And then game night has been actually a really big part of our group. Not huge, but it's kind of nice to have some downtime. And it's definitely helped us get closer as a group, especially during this whole like virtual period. So the games like Categories, Jackbox is a favorite. I know Codenames is also a fun one. So yeah, we kind of do a little bit of everything. Yeah, so our goals for the year are kind of finalizing the turbine circuitry. I know that recently we kind of tried to plot out ideas that are, kind of necessary to the process, might be a little extra if we have the funding or time. And then there's some, dream features, but we definitely want to use more of the Arduino to display things like battery percentage, light indicators, which would be great to kind of let us know in advance of, either errors or positive things. So yeah, that's a huge part of the process, and we're happy that we have an electrical engineer on the team to help us out with that. We want to have complete SOLIDWORks models of both the vertical and horizontal turbines. Just to kind of have it in virtual form is kind of cool, and it it helps the actual building process when we can eventually get to it a lot easier. And so yeah, in the springtime, hopefully when all this is hopefully done and dusted, we have no idea, but we kind of want to start prototyping and building it up again, because spring last year was when a lot of us were getting kind of ready to construct it ourselves. So we've been using the time to kind of just, polish up and see if we can improve it in any shape or form. And yeah, we kind of want to get going again. So we'll just have to, get the green light for that. But yeah, we just wanted to thank our sponsors again. So the Green Initiative Fund, we have the Triton Engineering Student Council, and of course, AIChE. So yeah, thank you guys. And if you have any questions, feel free to ask.
I don't know if we have any time for questions right now, but yeah, hit us up in the poster session.
Yep.
Since we are a little bit short on time, let's go straight ahead into AWT.
Okay, give me 1 second. Is it working? Can everyone see my screen?
Yeah, we can see your screen.
Okay, cool. I'm gonna make this real short, people. So hi everyone, my name is Breege.
And my name's Haley.
And we are the project managers of active water treatment. Our team basically aims to alleviate the substandard health and living conditions in the Navajo Nation by cleaning their water supply of its heavy metal and nuclear ion contaminants. And this is our team, group of lovely people. Next
slide. Okay, hi, my name's Isabella, and I'm a process engineer for AWT, and I'll start off with the background. So when uranium was discovered in the Navajo territory in the 1940s, the US mining companies began extracting the uranium from the Navajo Nation for over 4 decades to keep up with the demand for nuclear energy. The improper closure of these mines has allowed uranium to seep into the surrounding landscape, polluting the soil, air, and water. And according to the EPA, the maximum contamination level of uranium allowed in water is 30 parts per billion, but some of these sites have up to 700 parts per billion of uranium. Next slide, please. So this is a problem because the uranium ion is known to cause increased rates of cancer, organ failures, and hereditary birth defects in the Navajo population. And this also causes a huge disproportion regarding the access to water when we compare how the average American uses about 80 to 100 gallons of water per day, while an entire Navajo Nation family only gets access to 7 gallons per water daily.
Hi, I'm Mika. I'm a process engineer for AWT, and I'm going to talk about our proposal. So basically what we're utilizing is ion exchange, which is where there's an absorption of targeted ions with a solution using resins. We plan to utilize like a ion exchange column filled with like negatively saturated resin beads. The uranium in the well water is formed with negative ion complexes. So when contaminated water goes through the resin, the resin would actually displace the uranium from the water, so it's free of uranium once it passes through. Next slide. So what we're planning to do is like modify the traditional approach. So traditionally, there's a huge chemical plant that all this water has to be treated through, but we want to make it more portable and more accessible for the Navajo Nation. So we're planning to downsize it and make it so that can fit in the back of the truck.
The slide changed, right? Okay, sorry. Okay, so our current build right now has a 1 tank, an ion exchange column, a pump, and piping. What we plan to include is a pre and post water treatment, because not only do we want the water to be potable, we want it to be drinkable. So our pre-water treatment is going to be this activated carbon filter. So it uses chemical absorption with like increased surface area to remove impurities such as silt, odor, and color. This is also like a really effective and fairly low cost method to just enhance the drinkability of the water that we're treating. Our post-treatment is going to be UV lamps. So in order for the treated water to also be drinkable, we also need to remove microbes. So the ion exchange column is super effective at treating dissolved ions, but it doesn't really have any effect on microbes. So that's why we're going to use this UV sterilization. And it's fairly simple. We put UV lamps in our tank, we turn on the UV lamps, and then the microbes die. It's used to treat a lot of things. Sorry, I need to do better at this. So it's like low energy, pretty cheap. It's used in like homes and aquariums right now. And there's easy maintenance. So, and it minimizes the like chemical byproducts.
So basically we're gonna put the pre-filtration system and the post-filtration system on our current build. So as you see here, we have the activated carbon system, and then we have our UV lamp inside of a second tank. And then next slide. So we plan to use the Bernoulli's equation to look into how our pressure is affecting our system. We don't want too much of a pressure buildup. We want to make sure our pressure is consistent and is able to be like filtered throughout the system. Next slide. And then finally, like our future plans, everything's really different with COVID. So we're trying to find creative ways to keep going. We were in the building stage. So now we're looking into CAD models, improving that for our new system, funding, looking further into fluid mechanics, our resin, and hopefully next summer we can actually build our second system. So thank you so much. If you have any questions, find us in our poster session.
All right, that's fantastic, AWT. Thank you so much. And thank you to all the teams for presenting. I really enjoyed seeing everyone's fantastic slideshows. So let's move on real quick. I'm gonna move a little bit fast because I want to get you guys to poster session. Can everyone see my slide?
Yes, we can.
All right. So we just wanted to take a minute to talk about our fantastic awardees from Spring Showcase. Active Water Treatment won both Best Team and Organization and Best Poster. Portable Wind Power won Best Team Dynamic, and Photonic Fabrics, who was a team that graduated last quarter from projects, won Best Presentation. On top of that, David, Arun, Joyce, Daniel, and Brandon, thank you all so much for everything that you did for your teams. We wanted to mention you all in this showcase welcome night because we have certificates for you now, and they should be coming out to you. Look out in your Slacks, look out in your emails. They should be coming in just a couple of minutes. So yeah, congrats everyone. Many thanks, many thumbs up. And we're going to move on to the next slide now. Diana, would you like to take it away?
Okay, moving forward for all of you who are here that are not on project teams currently, sorry. If you are interested in applying, I will also drop the link in the chat. There's also the QR code for you to apply. Applications are due next Tuesday, November 10th by 11:59 p.m. Please don't miss this deadline. And we also have a required interview day with those teams on Saturday, November 14th from 10 to 2 p.m. So please keep that slot open if you are interested in applying to any of these teams. You are also strongly encouraged to go to the poster session, get to know your teams, get to know your PMs, and best of luck to you all.
And real quick, we have a Chipotle fundraiser in 2 weeks on November 21st from 5 to 9 p.m. It's going to be the Chipotle near campus, near Ralph's and Trader Joe's. Be sure to tell the cashier when you go there that you're with AIChE Projects, and these funds are going to go to help our project teams and carrying on further research. And also, real quick note, order through Chipotle, not through like food delivery apps.
Right, so before we move on to the poster sessions, just a few instructions, ground rules. Each team will have a Zoom breakout room. So with the new Zoom feature, you can hop in on whichever breakout room you want to. Once the breakout rooms are open, in the lower bar of your screen, you will see a breakout rooms button. So once you click on that, you can choose whichever breakout room you want to go to. And we encourage everyone to keep moving between breakout rooms every 10 minutes or so that everyone has a chance to talk to as many teams as possible. And so yeah, with that, let's commence with the breakout rooms.
Also, just in that we might go a few minutes over time just because we did have those technical issues. But yeah, enjoy the breakout rooms, everyone. So thank you for joining us. Please make sure to sign in if you haven't already. If you have any questions for leadership, drop them in chat. We will be hanging out for a few minutes after the event. Thanks for hanging out with us for a few minutes after the event already because we went a little bit over time. If you would like even more AIChE, we have all of these social media accounts from Discord to Facebook to Instagram. We have a LinkedIn account. We haven't listed all of them here because there's just a lot. But please check us out everywhere. We're always excited to hear from you. We have a lot of events coming up and they're all very exciting. So we hope to see you there. Other than that, I hope you have a great night. Thank you for coming. I hope you had some great conversations and learned a lot. Thank you.